Hey everyone, so time to do this. Let me know if the mic volume is okay. Haven't done this in a while, so I hope everything still works as expected. So we're in for a long one today, I hope. Hopefully it won't be like 3 hours, but I'm not going to promise anything. So let's just jump right into it. So it's kind of weird to keep doing introductions on these streams. Just for anybody new, just a quick background on me. I've been working in AAA for roughly a decade now, primarily gameplay systems, animation, AI, 3Cs, that sort of thing, as well as a lot of like engine work. I've actually been focused on animation for the most of my career, and so I've been lucky enough to actually build an animation graph, an animation system multiple times from scratch, and kind of have it trial tested by people on the team and have it used in production and that sort of stuff. So every time I do this, I basically end up stripping a ton of code, stripping a ton of features, stripping a bunch of stuff, because I realized that, I overthought something or I made it too complex or nobody needed that tool or it was never used or it just confused people. And so this talk will basically just kind of explain what an animation graph is, how to kind of build it, and I'm basically going to just explain what my version of an animation graph is inside of my home engine. It's very similar to what I built at work, which is being used in various, AAA, whatever scenarios. That's sort of it. The overview of this talk will primarily cover how to build a graph runtime. We're going to cover, how to build a hierarchical finite state machine. It's going to be a very kind of flexible, extensible graph. It's going to be high performance. We're going to discuss how to integrate physics into the graph. And IK, we're going to talk about how to do some LOD stuff with pose calculations and that sort of thing. So it'll basically give you like the high level overview of how to build an animation graph if you want to do that. I'm going to try find a way to share my code, but it's tricky because it's part of like my engine. What I might do is just strip it out and just put it up in GitHub. It won't compile anything, but it could be a reference for people to use. If there's any interest, poke me on Twitter and I'll figure out some way to do that. So let's talk about gameplay animation first. I did a previous stream on animation basics. It's worth watching that first, but I'm going to just fundamentally talk about how animation is used in games because the animation graph system is fundamentally how we take that low level stuff and we present it to users both on the game side and then how it's actually used in the game for the end product. So the basic flow is that you have game code that runs some sort of a game simulation, AI, player inputs, whatever, and that gets converted into a gameplay state. And that gets forwarded to the animation system, which then basically takes that input, does something with it, and then spits out several things. The primary one that everybody thinks about is the pose. So that's like the actual animation of the character. But there's two other very important things. The one is the root motion. It's like, what did those inputs result in? What kind of a movement did that result in the character? Secondly, if there's any events like, oh, do I have a contact event? Should I play a VFX? Should I holster a weapon? Is my thing done? Should I trigger a damage event? Those kind of that kind of information that comes from the animations themselves. And those will then go back into game code. So the pose will be applied to the 3D skeletal mesh. The other two things will go back into game code, and then game code will basically say, okay, I know what animation's done. I have the root motion, whatever, so I'll move the actual simulation object in the game, the capsule or whatever you're using. And then it will also then trigger any additional stuff that needs to be done, for example, an audio event or VFX, damage shape, what have you. So what an animation system should do, it should generate a pose for the animatable object. It should sample all the animation events needed for a given update, and it needs to provide information about the root motion. Right? Those are the three basic things that it needs to do. There's an extra one where it needs to provide information about what it's currently doing, but we're going to go into that later. What it shouldn't do is it should not be modifying gameplay state directly, and it shouldn't be moving things in the game directly. I've seen this mistake a lot of times in that there's no boundary between animation and gameplay. And so as part of your animation update, you're modifying the gameplay scene. So not only is gameplay providing inputs, then the animation system is changing that without gameplay being aware. And so you end up basically embedding your animation system with your gameplay code. And at that point, you have just a mess of dependencies, and it's impossible to debug because maybe an animator modified something. Now the gameplay coder is like, I don't understand why things aren't replicating or what happened. I set this thing here, now it's moved. The animation system should fundamentally just be a black box. It should be, here's some inputs, tell me how far you moved, what is your pose, what are the events, and then I decide what to do. So graphs. We're going to go on a bit of a history lesson here about how sort of things evolved over the last, it's been a while, call it 15 years-ish, longer probably. So back in the oldie times, it was a lot simpler. You would basically in gameplay code directly say, hey, play this animation. You know, if I'm running, play this run animation. If I have 3 run animations, I'll set the blend weight and I'll tell you, okay, it's these 3 animations, blend them. And so it was all code controlled. Whenever you switched gameplay state, you just basically just said play animation, you picked your new animation. Funnily enough, I think a lot of older school programmers still think that's how things work. And they kind of make engine decisions regarding, animation, but things have moved on significantly past that point. So obviously, as the games kind of grew in complexity, this can't really work. It became impossible to manage. You were basically writing blend trees in code. Every time somebody wanted to tweak something or integrate a new animation, it was a code change, all this kind of stuff. It was a mess. So the first major kind of paradigm shift was towards blend trees. And what a blend tree is, it's basically just a single tree that allows you to specify, here's some animations and here's sort of the operations that we want to apply on them. So you want to say, oh, I want to blend the jog and a run, and then I want to blend the directions in after that, or some degree of operations. This basically still allowed gameplay to say, hey, now I'm in the locomotion state, so play this blend tree. And then when I go to another state, it's this other blend tree, right? So a lot of the state management was still done in code. Some places extended this out in a really, I'm going to say aggressive way, where they basically built a massive blend tree that handled everything. I think some UE3 projects initially were doing this because there was no state machine, it was just a blend tree. So they would do something like is shown in the slide, where you would basically have all your different animation states in a giant blend tree. And then code would basically be controlling the weights in and out. So they would basically try to model a state machine in a blend tree by manually saying, okay, now blend in the kick and then blend out everything else. And then, okay, now I need to go to a punch and I'll blend out the kick and then blend in the punch, and they were managing these weights manually. And this was just painful to work with, really hard to manage. And again, there was a huge code dependency on this. So obviously the next logical step would be to move towards state machines. So we were already kind of like, some companies were already doing this. They were using a blend tree per state and code was switching it. So now they basically put the states into data. This really helps a lot because it's clear, like, okay, if I'm in locomotion, this is what the blend tree is doing, and I don't have to care about any state. If I'm in a jump, this is what the jump state does, and I don't have to care. So this greatly helps. But then with like the massive complexity and layering and a lot of these other things, this sort of also breaks down pretty fast. And you end up with like really complex blend trees, or you end up with like these monster state machines that everybody's kind of seen as like you know blueprints from hell or whatever. You see these kind of crazy animation state machines where everything references everything, it's just arrows everywhere, it's unreadable. That's the basic end point of this approach. So for example, like a very simple setup here, you've got your locomotion, you've got your attack states, you've got hit reaction states, you've got your jump states, those sort of things. And then now you start your transition stuff and you end up with sort of a mess like this. This doesn't work. So this just doesn't scale. And I think a lot of people kind of got to this stage, realized it doesn't scale, and then just wrote off state machines entirely. Whereas like if we carry on this logical path, well, the next thing is to actually add hierarchy into the graphs. And this sort of simplifies things a lot. It basically makes things a lot easier to reason about because you still have your high level states, for example, like locomotion, attacks, hit reactions, whatever. And so those transitions simplify because it's like, yeah, well, either I'm in locomotion or I'm doing an attack or I'm in a hit reaction. It's a lot easier to just understand where I'm in. And then within hit reaction, yeah, I might have multiple states there. And again, those transitions are like, am I in a flinch? Am I in a knockback? Whatever. And then you basically split your decision making into multiple levels, which makes it easier to reason about, makes it easier to debug, a lot of those kind of things. It also kind of makes it easier to manage your parameters because now your parameters to the animation system are sort of separated out by these kind of high level states. So you'll have a set of parameters for interactions, you'll have a set of parameters for locomotion, one for attacks, that sort of thing. And then it becomes clear who set what and if the parameters are correct, those sort of things. So for an animation graph, let's say we have a state machine. That state machine, you would immediately think it's like, okay, it contains all the logic I need to select and to play back the animations, right? I would go further and say it's to generate a character pose. It's not necessary to play back animations. To some degree, we need to stop thinking of an animation system as sampling an animation and playing back an animation raw. In some setups, yes, that's exactly what ends up happening. But in a lot of cases, we're taking animation sources and we're using them as input to other operations to procedurally sort of generate a pose out. It provides information back to gameplay about what animation state the character's in. This is very important to know whether I should stop a gameplay state, if I should transition, or if I should still wait, that kind of thing. A lot of times we'll say, hey, I need to do an attack, and then we'll wait in gameplay code to say, has the attack started? Okay, cool, it has. So now we wait for that to finish. When it finishes, then I can transition in gameplay. Or additionally, it's like, okay, what am I currently in? If I'm currently in this state, I can make different gameplay decisions. It also comes back to what I mentioned with the events. It feeds back information back to gameplay and other subsequent systems to do visual flair, that kind of stuff. So how it should be built, in my opinion, is you basically have a set of control parameters. These are the inputs to the graph. It feeds into a black box and you get back your events, your root motion data, and I'm going to say pose. The pose isn't actually calculated via the graph in my setup. I'll explain that in a later thing, but fundamentally it's those three things, right? That's what should happen. It's just a black box. You feed in some inputs, you get back some outputs, then you figure out what to do with those outputs. It doesn't make any decisions. It doesn't do anything. So primarily I have two types of nodes. I'm calling the one a pose node. I used to call them animation nodes before. The naming is a little bit tricky. Basically what they are is the things that manage time. They're the things that will sample an animation and send back a command saying, hey, I've sampled this animation to calculate the pose. They will read the root motion from the animation clips. They will sample the events and they will pass them up the chain. Basically, they are nodes that will output a pose. And I say pose, I mean kind of a pose result. And we'll see how that gets used in later on. And these ones are basically that output can only go into a single input. Additionally, I have value nodes. These are basically just, ints, floats, that sort of thing. They don't have any real state. They're just a value. And they can be connected to multiple connections. It doesn't matter. The value nodes also have a mechanism where they're calculated on demand. You might have a whole chain of, let's say, mathematical operations of take two floats, add them together, multiply a bunch of things, those sort of things. Shit, I forgot to put it in a screenshot. Whoops. But basically, what it does is, and I have an example later on where I'll show it in the engine, is when you ask a node for its value, if it hasn't already calculated it for that frame, it will lazily calculate its value and then return that. Any subsequent request for that value will just give back the cache value, because within the context of a single update, nothing can change because you have a set of fixed inputs. You call update. Within that update, everything's immutable. So we basically can cache the results and skip entire long chains. You'll see when we have a lot of complex transitions how this can be a massive performance win. I have a set of basic value types like a bool, obviously, an ID, which is basically just a string ID, an int, a float, a vector, a target, and a bone mask. So we're going to talk about the targets first. That's a kind of custom type. Often we need to tell the graph, hey, I need you to basically, what's the word? I need you to jump to this point, or I need you to interact with something at this location, or hey, you need to offset, IK target to some degree, or hey, this is your actual IK target. So we need to give this to the graph in a meaningful way. And a lot of times that is just a transform, but other times it may be a bone ID because we want to target a specific bone in the pose. And so the target basically is a wrapper to allow me to specify some sort of a location and transform, and the source can be varied from either a transform, or it's like telling the system to basically say, hey, look at your actual pose and get the value from the pose. This is sort of, again, very useful when we get to how the poses are calculated, because it also allows me to control that target if it's read from the previous frame's pose or the current actual pose in a chain of pose operations. Control parameters, they're very simple. They're just value nodes. We don't allow bone mass as control parameters. They're set once. You call the update for the graph. You can read them back. I don't see a point. You have set them already, so you should have those values. They are unique names, and gameplay code basically binds to those parameters by name. So they have a graph instance, and they basically say, hey, I need parameter speed. And they get back an index, which they can cache, and then every time frame, they can set the speed via that index. We have another feature called virtual parameters. So a lot of times we will feed in stuff from gameplay like, hey, this is your speed, this is your hitting, you should jump or you should fall, or this is your speed in the air, those sort of things. Now, a lot of times the tech animators will need to actually take a set of those parameters and generate another new sort of compound parameter from that. They might say, hey, my speed in air is this, my velocity is that, I've been in the air for this long, so what I want is a bool that says I'm in a heavy fall, and so they would basically define this via a virtual parameter and say, hey, combine these control parameters in a specific way and output a value that then I can use as it was a control parameter in the graph. Now, gameplay code could do this, but a lot of times it's just easier for them to manage it because, a lot of the time they need these for visual changes, and it's entirely dependent on how the graph has been built. And so we give them that functionality. Again, this is where those value caching comes into play, where the first time that parameter is accessed, we calculate the value. Any subsequent requests to it just read the value directly. There's no more calculation. So you could have a really complex calculation for the value parameter. It does not change. It only gets to run once per update. This is kind of what a value node looks like. I just have basically some type validation, but it's a very simple thing. As I said, I can make the code available. One thing that's important to note is you'll see there's virtual functions. And I'm sure a lot of people already like, what the fuck? But everything uses virtual and polymorphism. And when you see the performance numbers, you'll be kind of surprised. So moving on to the pose nodes, these are kind of the primary nodes for what you would conceptually think of as an animation graph or a blend you would need to do. They basically track the time per node. They manage synchronization, which was covered in the animation basics. So basically, again, it's a time update mechanism. They then register pose tasks. Basically, when you sample an anim clip, it doesn't actually read a pose. It basically records a command, like a GPU command buffer saying, hey, you need to sample this animation at this time. And it records that in a kind of command queue. It will then sample and modify root motion deltas potentially. It will get the events and that kind of thing. So you can kind of think of each pose node as sort of an animation. It has a duration, it has a sync track, and it has a previous and current time. That's sort of what it looks like. I think it's kind of, the code is kind of useless to show to some degree. But the important thing here to notice is that you'll see that the information we track per pose node is fundamentally the loop count, the duration, and the previous time, and where we're currently at. If you look at the pose node's result, that's the first struct defined there, you'll see that, there's a task index. The delta that was sampled at that node, and the sampled event range. So we have a giant event buffer that we fill as we proceed through the graph, and each node basically says, hey, this is the event range that I sampled. And that is passed back via the update function. So whenever a node is updated, it returns back what it did. And then that gets processed, modified, and passed back up the thing. So at any given point when you update your child, you have the information of which events that it sample, what's the root motion from the child, and so on. Pose nodes also have two updates. There's an unsynchronized update, which basically just takes the time delta for that update and just says that's what you step with. So you update your time with whatever the time delta is. There's also a synchronized update, which basically gets the explicit time range for that update. So it doesn't track previous next. It basically gets told you started it here and you will finish at this point, and that's what your update is. And this is how we actually manage synchronization, where we drive the time via let's call it a main node, a primary node somewhere else, and then every other node is being driven according to that time update. There's not many nodes that trigger a sync update. Fundamentally, it's either transitions or blends. Layers are essentially just blends. So those are the three things that will basically switch between unsync to sync. Pose nodes, as I said, will register the pose tasks. They'll modify the time deltas. They'll get the events. We have one more kind of concept. All of the nodes, whenever they get updated, they get passed a graph context. And what that context is it provides all of the necessary data for that instance to execute. So it will have something like, here's the task system that you're registering your tasks into. Here's the event buffer that you need to fill with your sampled events. Here's the will transform from the character this frame. Here's the pose from the last frame, that kind of information. And that gets passed through and gets used by each node. Additionally, they're tracking the data set, which is something we're going to get to shortly. The last kind of major concept in the graph is something I call a source node. They are basically like a slot where data can get plugged in. So for me, the graphs themselves are just logic. They do not contain any reference to any data. They are just logical operations. I have two animation clips here. They get blended this way, and then the result gets sent into a layer and gets modified in that. We do not reference any data. The data is provided as from the outside per instance, and it's passed in via the context. So for example, we'll know the data set in the when we create a node, we'll say, here's your data, and it fills the slot at that point. This is really useful when you want to do multiple variations on the same graph. This is fundamentally done through what I call animation datasets. I used to call them variations in the past, but it gets complicated. Basically, imagine I have a very simple blend tree of like 6 animations. The graph is the logic. I have those slots. So I create my graph, and then I basically go into a database and I fill out those entries of saying, hey, you know, jog L, it's this animation. Jog F, it's this animation. Jog R, it's this animation. And then when I run the graph, I basically say, hey, run this graph with this data set. And when we create the instance, we fill out those nodes. Now, what this allows us to do is basically do hierarchical derivation. So we have a default data set that always exists. And then what we can do is we can basically derive from it and do something like, hey, I want to have now a grunt, and the grunt will override this set of animation data. And then from the grunt, maybe we have a different variant like the power suit, and he has a different walk cycle. So I just want to override that walk cycle, you know. And so we can basically build this sort of derived data sets. And when they get compiled, they just get flattened into a flat list. And so when we instantiate no, we just say, okay, it's this graph with this variation or this data set. So just fill it out. I'll kind of show you what it looks like. So for example, I've got an example graph here, and I've got basically a default variation, which just has actually 2 animations filled out and everything's empty. And if I switch to the grunt, you can see that I've actually overridden these animations here in that version. If I want to, I can add an override here. I can reset it back to the default. If I want to, I can clear animations in a derived version that were set. So for example, I could go here and just override it. Oops. This sort of basically allows me to control what gets set per archetype. So for example, like part of my state machine may have, you know, logic for a very specific use case that only maybe 10 of my AI have, 10 of my AI archetypes have. But I don't want to now split that out into an external graph and do a bunch of crazy stuff. So I'll just leave it in the graph. I'll just clear the data, and only the archetypes that need that feature will have data sets. So I'm not loading any animations that I don't need to. So it's a good way to kind of manage what data you load and, you know, what archetypes reference what. Another thing I mentioned is that the nodes can modify the root motion. So basically what a node will do is when it samples the root motion, it's pretty much root motion can only come from a single node in the graph called the animation clip, and that's the thing that actually operates on animation clips. Every other node will just get past its child results, and then it can take that root motion delta and modify it. So for example, we have a root motion override node here that basically allows us to take a root motion from its child and just override components of it. So you won't be able to read the code, but you know, afterwards the slides or whatever will be available, so you can go into a bit more detail. Basically just says, hey, I want to take this root motion delta and I want to modify the heading, you know, I want to adjust the velocity. Or I want to completely remove the Z from the facing. Or I want to, you know, multiply out the translation by X amount. So it allows you to sort of apply those modifications within the graph and just pass it up to the parent. Another example of a node that we have is speed scaling. This is a very commonly used tool to basically adjust the velocities of certain animations, how fast they run, those kind of things. Basically, all it does, it operates in a very simple way, is it says, okay, what's my delta time? I multiply the delta time explicitly, and then I update all my children with that modified delta time, and then I reset the delta time. This is from my home engine. So for example, I modified the context directly. At work, I had built a guard value to make sure that, you know, mistakes didn't happen with people accidentally forgetting to reset that. If you built this in a production sense, you probably want to do that. You'll notice that the synchronized update here, for example, throws a warning. Synchronization, as I mentioned, is an update where you're saying, I am controlling your time explicitly. You started at this point and you end at this point. You cannot scale that. You cannot modify that. It is exactly what has been told because that is you're running in a synchronized mode. Now, that warning is probably a bit aggressive because there are multiple use cases where you will run a node in a synced update. For example, you'll run one blend tree in a synced mode for a few frames, and then you'll switch back to an unsync. So you will get that warning for a few frames, and then it'll go away because it goes back to the non-sync update. This generally happens when you're transitioning. You might start a sync transition, and when that transition ends, you're now running unsynced. So that warning's probably a little excessive there. So blending, let's talk about a bit about blending. A lot of NM graphs out there often have a lot of different blend nodes. Some even have like blend spaces and a bunch of other like mechanisms to blend. Over the years, I've been through that whole thing. I've suffered with building 2D blend spaces. I even went down the path of 3D blend spaces at one point. I do not recommend. But in general, over the years, I've basically just moved away from everything. I think it's all just tech looking for solutions. Fundamentally, the order of blending will change your pose, right? That should be obvious to anybody that's ever blended animations. The order in which I perform certain blends will change the results. A blend space basically tries to build a space for those animations and to define the blend weight between them based on a parameter. The issue comes in if you do this automated, the animator will at some point ask you saying, hey, I actually want to blend these three animations in a different way. As soon as that happens, now you're in the process of, I need to provide painting tools to actually hand author the blend space. Because I can't just generate the thing automatically. So now I have to provide a tool. And once they start doing that, well, at that point, it's like, what are you even doing? How is this tool helping anyone? The reality is, what you want to do is you just basically want to specify how do I want to blend this set of 6 animations together, in what order, and which animations blend well together and which ones don't. And the animators know this inherently. That tool is just a pain in the ass usually, because now they have to try to understand what they're seeing. How does this map to what they kind of inherently know in their mind? I've just never seen a benefit to this. Additionally, it makes the anim data set overrides really complex because the parameterization is generally based on the data if you're doing the automated version. So now you're also storing the parameterization inside of the data set, which complicates that compilation step. You have to be able to preview. It just makes a big sort of pain in the ass across the board for little to no benefit. So what do I have instead? Well, I just have a range blend. I have a 1D parametric blend. Users basically say, these are my animations. These are the ranges for the parameter that these animations map to, and it will just calculate the blends for them. This basically allows an animator to very easily say, well, I have a speed. My jog is at 1 meter. My run is at 5. This is at 6, and basically I blend according to that. And it's very obvious for them. Additionally, what you can do is somebody's going to say, well, hold on, different archetypes, they have different speeds. You can't just put the speeds in the graph. Yeah, you can't. But it's very easy for a gameplay programmer to feed you a normalized speed. And so what they can then do is, 0 is my walk speed, 1 is my sprint, and my run is at, 0.75. And you can agree on a metric, and you can just set this up really easily. You don't need a bunch of machinery and boilerplate stuff to kind of predict all this shit for you. I have a secondary node called a velocity-based blend. This one is primarily there to avoid the parameterization issue for speed, because it's just such a common use case. So all that it does is it's a 1D blend that the parameterization is calculated from the animations that you plug in. It's just a syntactic sugar. Those are the only 2 blend nodes. Now, I've worked in some animation systems where you say blend and you have a list of like 30 blend nodes, because every time somebody needed something explicit, some programmer went in and hard coded a bunch of stuff in a blend node, which could have just been done using a very basic set of tools. Or they worked around missing features in other areas of the system by providing some crazy bespoke blend node with some random name that one animator on one project understands. I mean, I worked on one animation system where half the nodes, nobody knew what they were because they were built on a different project. And then this animation system was integrated. So now nobody had a clue what they meant. And so they basically built their own set of nodes that did similar things. And it was just a giant mess. And for the users, it was impossible to reason like, what the fuck do I use, when, how? Whereas with this approach, it's like they have one blend node. It's a very simple thing to use. This is kind of what it looks like. You just provide as many inputs as you want, and you specify the parameter ranges for them, and Bob's your uncle. It's super easy. It works. Let's talk about state machines. Sorry if I'm going a bit fast. I have a lot of slides to go through. As I said, I have a hierarchical state machine. Each state is a blend tree, and each blend tree can have multiple state machines within it. So there's no limits to the depth of the hierarchy as far as you want. And in fact, I'm going to say that it's perfectly okay to have deep hierarchies. Go as deep as you need to if it solves your problems and it simplifies your setups. We've had hierarchies that were almost 20 levels deep. At like where I was working before on that game, and it worked just fine. There was no problems with it. Just leverage all the tools you have, and yeah, there's no issue going deep if it solves the issue. Now, the transition node is kind of your animation system fundamentally in a state machine graph. It is the core of everything. And it is actually the most complex node, and by far the most code. I think in my case, it's something like 700 lines of code, mostly to calculate the initial starting point of the target state. And every other node in the graph is like maybe 50, 60 lines of code. And this is kind of the heavy lifter because it's the primary thing that you are doing. It basically controls several things. The first, obviously, being how long should it last for. Generally, transitions are relatively short. They're like 6-7 frames usually, 0.2 to 0.3 seconds. And the key thing that it does is, where should I start the target state from? And there's a whole bunch of options there. Should I match the events? Should I match the percentage? Should I just start it from the beginning? Should I do a sync update? Those kind of things. It also can step the time synchronized. If I'm, let's say, blending from one cycle, like a walk cycle, into a jog cycle, it will blend synchronized. Additionally, it has controls over saying like, hey, while we're doing this transition, what do I do with the root motion? Do I keep the source and the target and blend them together? Do I only use the target's root motion? Do I only use the source's root motion? In many cases, that's necessary to ensure that characters end up in the right location, because during the transition, the blend can fuck up things that you have maybe predicted. For example, if you're warping a specific animation in one state and you blend out, you want to keep that warped root motion. So you will basically ignore the target state's displacement until the transition is over. That way you'll be guaranteed that you end at the right location. In my engine, within the graph view, every transition is what I'm calling a conduit. And each conduit can contain multiple transitions. Conduits can also be left empty, and you'll see why that is. So you'll see in my case, like I also have a dual view, and this is something that I find really important to kind of work with the graphs. It's something that I haven't really seen in many places, and I don't know why, because it simplifies matters greatly. So if I open up a state machine, I can click any one of these transitions and they'll show up at the bottom here. So I can see both my state machine as well as the thing that I'm editing simultaneously. So I don't lose context of what I'm currently doing. So I'm saying, okay, I've got my idle to walk state transition. It's this transition, and I can set whatever settings I need to set on it here. You know, whereas in a lot of places, you would double click the transition and then you would lose context of where you are in the graph. This also allows you to quickly go between and say, okay, I want to copy stuff from here, put it here, maybe go to here, look at the setup there. All right, let me just check this one. Yeah, it's the same. Okay. You maintain context of what you're editing. And that is extremely important. And it's not something that I've seen done a lot of times, which is annoying. So let me just make a new state. And there's other cases where I use this as well. You need to excuse the way this looks. I haven't spent much time making it really pretty. So let's see, what am I looking for? Sorry, I'm an idiot. Selector. You'll notice that I have a selector, which is basically an if statement. And again, I have this, I referenced this dual view where when I click the selector, it shows up in the bottom here, and I can basically say, hey, I want to actually use the speed. And if the speed is, I don't know, greater than 0, then I want to pick option 1, else I want to pick, option 2, for example. And again, I have that view. So when I click the selector, I see immediately what the conditions are. I don't know why this isn't done anywhere else. I've never seen it before. I hope if there's one thing anybody steals from this talk, it's this. Please just do this. It's a massive help for everybody. So as I mentioned, that my transitions my conduits can contain multiple transitions. This is often needed because between two states, you may have a different need in terms of what the transition should be based on the current game state or the current state of the graph. So sometimes I might have a default transition. I may also have a very fast emergency transition where, for example, the default one would wait for the animation to get to a certain point and match an event and then transition, versus us telling it, go to the state now, right now. And at that point, it will directly just fire a different transition. That's like maybe a pop-up pose and a 0-frame transition, whatever. Sometimes you want to control where you would start into an animation due to synchronization or just trying to match foot event to that, even if you're not synchronized. I have a very simple example. This is from the previous talk I did, where basically we have a very simple jump. And we've decided that we want to make our jump route motion driven for whatever reason. So our jump animation basically has a launch, and you fly in the air and then you land 50 meters away from where you hit, the apex of your launch. Now, how would we build this into the graph? Well, the first thing we would probably do is we would split that into two chunks. We would have the launch, and then we would have the sort of landing. And then somebody's going to say, well, like, it's great that the jump goes 50 meters, but potentially because it's animated and I want to control it, I want to be able to say, hey, if I'm jumping between two platforms and the platforms are 5 meters apart, I want to only just jump 5 meters. I don't want to jump 15, or if it's 10, I want to jump 10. I don't want to go 15. It's not exactly what I'm looking for. So what we can do is we can create multiple transitions between these two states. We can create one for 5 meters, one for 10, one for 15. And what we will do is we'll create sync periods for that animation. We'll basically make one period that covers the first 5 meters, one that covers the second 5 meters, and one that covers the remaining portion. So that animation now has 3 sync events. And what our transitions will do is basically say, hey, if I want to just jump 5 meters, well, just skip the first 2. The 10-meter one will skip the first one, and the 15 won't do anything. So you'll notice there's a sync offset on the transition node. You can basically just tell it, hey, when you go into the next state, offset the initial time by 1 sync period. There's other ways to sort of control where the target state will end up. You can match a sync event, you can match the percentage through a sync event, those sort of things. So you have a lot of control for how to go from one state into the next. This is also an area where you can see, for example, our transition conditions potentially reuse a bunch of information. For example, the ID comparison is used in 3 transitions. The target info is used in also 3 transitions. This is again where the value caching comes into play, where, for example, the first time I evaluate the 5-meter condition, that frame, well, the ID comparison and target info will be cached, and the 10 and the 5 won't need to do that work. You'll just have the value directly there. In previous animation engines where I've worked, transition conditions, just evaluating them tended to be one of the massive costs associated with the runtime. And in my case, it's not a major issue, primarily because I'm shaving the values. In a lot of places, each transition basically is redoing the same operations multiple times. This allows, for example, tech animators to do almost like functional programming. They'll not functional programming, but they'll program in like sort of functions. They'll build a set of conditions and then feed that to multiple transitions with some additional parameters and stuff. And again, it's been a very simplified way to do it. And I'm just surprised that nobody's really doing something like this. So there is another concept with transitions. Like imagine I have two states and they can go from one to the other. If I'm currently in state A and I start a transition to state B, and that transition might be very long, for example, half a second or a second for some reason. But while I'm now transitioning to B, all of a sudden I get a signal, hey, you need to go back to A. And it's not that common that this happens, but there are enough cases that you need to handle it. So what are your options? Some anim systems, they basically create the nodes dynamically. So whenever you go into a state, they will instantiate a new instance of that state, create the nodes, and trigger the transition in and do that. In those kind of systems, this is okay because you would basically just keep instantiating these states as you need to. So you'll be in A, you'll have an instance of A, you'll transition an instance of B. Oh, you've got to back to A, so you'll create another instance of A. So now you have two instances of A running. And now if you go back to B, well, you can create another instance of B, and now you have two of each with like multiple transitions. This personally, I think is really stupid. It's extremely expensive. You're constantly recreating nodes and states and whole sub hierarchies. It's nuts given the scope and the size of these graphs. It's insane to do this. Secondly, you're constantly allocating memory and you're freeing it, which can cause fragmentation in a lot of cases. Thirdly is you can cause infinite loops out of memory. That's happened in multiple places where an animator messes up a transitional logic and all of a sudden in 2 seconds he's out of memory because the thing has spawned, I don't know, 50 million instances of these two trees. In my animation system, we pre-allocate everything. So every node is instantiated at startup and has a fixed piece of memory and nothing gets changed, nothing gets allocated or reallocated at runtime. My transitions are also nodes, so they get instantiated as well. So in my case, I have A and B. And if I transition from A to B, both states are running, they're maintaining their state. And if I want to go back from B to A, now I'm kind of screwed, to be honest, because A has already got its state, it's already running. I can't, restart it and manage two sets of state. Now, what I do is I have something called a forced transition. By default, in that situation, I just in the graph block the transition, say this is not an option for you. You cannot go back to a state you're currently in. In special cases where this has to happen due to, I don't know, replication or something else, we have a mode where you can enable a forced transition. You have to go and you have to set this up because it does a bunch of other stuff under the hood. How it works is what we do is when we trigger a transition, we start caching a pose at A. So the transition itself will basically say, hey, I'm going to cache my source pose. In addition to calculating and doing all the blend stuff, I'm going to cache that value. And what will happen is if we need to go back to A from B, we will stop the A state. We'll just shut it down. And then we will just start a regular transition from B to A as if A was not running. But the transition from A to B still needs to continue. So what we do is we use the cache pose from the previous frame and we maintain that cache pose for the duration of the transition A to B. I don't know if that makes sense to everybody. Basically, what we're doing is whenever we fire the transition, we shut down A, we keep the last result of A, and we continue to blend that transition from A to B. Basically, it's like we're blending with a fixed pose for that few frames. Now, yeah, so I kind of forgot that I had these slides. And as I said, as we go from B to A, somebody will immediately say, hold on, but like you're now losing the motion because your cache pose just doesn't update. It's a fixed pose. The thing is, as the transition is proceeding from A to B, the weight on that source is decreasing. So in the basic case, when I'm going from A to B, my blend weight is shifting from zero contribution of B to full contribution of B. And A is dropping from 1 to 0. So as that transition proceeds, the weight of that source pose diminishes. If I'm now running a secondary transition away from that as well, it's exponentially decreased again. Because now B overall has its weight decreased, which affects the source of A. So it rapidly fades out of the actual contribution for the final kind of pose there. Additionally, our transitions are often really short. So this is almost completely unnoticeable. In fact, coming to the next slide, we had a fun discussion where there is this concept of using inertialization, which basically tracks the velocities at each sort of frame. And then when you have the situation, it basically continues the transition with those velocities. And I remember having a sort of an argument with some of the tech engineers. They're like, oh, we need this because I saw this GDC talk and blah, 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 and whatever. Now, I push back because one, this is expensive. It's really complex to do because you're basically semi-running a physics sim in a kind of way. Secondly, with really fast animations, it's going to keep limbs moving in that direction, even if they're not supposed to. All right. So if the animation started with an arm coming in sideways like this, and then at a specific frame flipped out to the left, you're just going to have that arm go straight forward. Right? You don't have control. You just have a velocity and you just run everything at that velocity and you run some parameters and you try to hope it looks good. And if that blend is long, you're kind of fucked. It also has issues with the root motion because, well, what do you do with the root motion? Do you just keep the last delta and just keep applying that? That could do a lot of damage in your graph. Additionally, it sort of solves the wrong problem. If I remember that talk correctly, this was also, they came up with this approach as sort of a workaround for very slow transitions. Their animation system was extremely slow in terms of evaluating graphs and that kind of thing. So this was a fast way of like, oh, when I'm in a transition, I kill that source state and I don't have to evaluate all that stuff, so I don't have to pay that cost. So this is cheaper for us. In my system, it's so lightweight that this is a non-issue. In fact, the initialization will probably be way more expensive than just running the actual source update. The cache pose, when we implemented it, nobody could even tell because fundamentally, again, we're trying to force something weird and we're doing it over the course of 2-3 frames. Plus with the blend weights and stuff, you don't notice it. And you don't have any issues with, okay, it's now doing the wrong thing. It's a weird pose that I'm blending with, or the root motion is now fucked, or whatever else. So, and again, this is kind of the thing where it's like, yeah, it's a fancy thing, but what are you trying to solve? What's the actual problem you're trying to solve? So, moving on, layers. This is another really fundamental concept. Every good animation system needs a layering mechanism. You need to have a way to modify the pose via a layer. It's just an essential thing. What we do is we reuse the state machines in my setup to do the layering flow. We don't have special tooling for layers. We have a node that basically says, hey, I'm a layer node, and I will let you layer a state machine onto whatever you want. So you can specify how many layers. It doesn't matter. You can put layers on top of layers. You can take a layer node, put it in a layer node. There's no restrictions on this in any form. Layering is done at sort of a local level. It's not global to the graph. It's not like the graph has layers. Basically, once you see the UI, you'll know what I mean. Fundamentally, for example, I might have an animation and I say, okay, within this blend tree, I have this animation and I want to put something layered on top. So I just put in a layer blend and I basically stick in a layer with some state machines to basically say these are the two layers. Each layer is a separate node. It doesn't do anything. This is purely a UI tool so that you can set up some settings and copy paste that node, which allows you to kind of move entire layer setups or quickly adjust them or reorder layers without having to work through a property grid on the layer blend. Again, a lot of solutions I have are fundamentally solved in tooling rather than in tech, because the most simple thing usually works best. My layers have some interesting things to them. You will notice that back when we layer, we only allow you to layer state machines. That's done for a very explicit purpose. Inside of every state, you can add additional information. You can add a layer weight and you can add a bone mask. So whenever you click a state, you'll see in the secondary view, you'll get the layer data. When that state is used, when that state machine is used within the context of a layer, that data is read and used. In the case when it's not in a layered situation, it's just ignored. What this allows you to do is you can now specify the layer weight on a per state level. You can also specify bone mass on a per state level. So imagine we have a bunch of very different layers in one state machine. So I built a state machine and I say, well, you know what? I don't want to create a layer that's upper body, and I don't want to create a layer that's full body, and I don't want to create a layer that's right there. I want to have just a layer with a bunch of actions. So what I do is my reload state will specify, hey, I have a full body bone mask. So when I ever go into this, I basically override the entire pose. I then have a flinch state, which if when I go into this, well, I basically am a full body, but my layer weight is adjusted based on some parameters. So for example, it will blend in fast and blend out fast, right? So I can control how much the contribution of that state applies to the base pose. Maybe I have an open door that now is dynamic because the bone mask can be manipulated at runtime too with a bunch of nodes. What we can do there is we can basically blend in the upper body first and keep the lower body from the base state and then blend in the lower body subsequently within that state. So we have that control on a per state level. Grenade might just be a right hand. So that gives the animator fine-grained control per state to manage the bone mass and the layer weights. Again, this is something that I haven't really seen anywhere else, and I don't know why. It's a very simple solution and it gives you a lot of flexibility and you can do some pretty incredible setups with this. Additionally, there's a concept called an off state within state machines. And what that means is that we basically allow us to turn on and off states via this, empty state. So all you're doing is you're writing basic state machine transitions saying, hey, when I want to turn a layer on, I basically have a transition from my off state into that layer, and then go back, and I can go from like layer state into another layer state, or I can turn off a layer entirely. This is a lot easier for animators to understand, or just actually not animators, for anybody to understand, because it's like, hey, I want to just turn on this layer. So is that layer an off state or is it in a specific state? It's super easy to debug. It's super easy to reason about. In the past, you would be managing layer weights at a different level or feeding it in from the outside. It was really horrific. And as I said, once you combine this with the per state bone mass and the layer weights, it becomes extremely powerful. Now, one thing that I don't necessarily mention here is that in that state with the layer weight, if there are additional layers below it, like an additional state machine with additional layer weights, those propagate upwards so they get blended. So you can actually define a layer weight multiple levels deep. They get consumed by the first layer node that they encounter. But if they don't encounter a layer node, that information gets passed back up at the state machine level and can be propagated upwards. So it allows you to, again, control things in a much more flexible manner. So let's talk about the tooling, which is kind of a really important part of this whole thing. And this is the part where a lot of people got away from state machines because they figured that, you know, the tooling was, the paradigm is flawed because they were working with shitty tooling. This is the example that everybody says, well, state machines are bad, right? Because I built this and it was impossible to manage. We ate shit with the project. Nobody could modify anything. Everything broke all the time. Yeah, if you built this, you're fucked. There are easy fixes to this. One is to use the damn hierarchy. And that one is common sense, which is also a feature. It's like, maybe don't build things like this to begin with. Secondly, it's tooling. If you provide some very, very basic tooling, you can fix this entire mess. So let's cover two elements that will fix a lot of this problem. First thing we have is called entry state overrides. Every state machine has a default entry state. It's the state that it goes into when it starts. But sometimes this isn't what we want. We want to go directly into a different state. And so what we provide is a mechanism to just basically override that entry state. So imagine you have a slide state machine, and you have a slide loop and a slide exit, which always has to be played. But depending where I was coming from in the graph, you would basically select which basic state you want to enter in. If I was coming from a standing state, I would go into standing. If I was coming from crouch, I'd go into crouched. If I was currently falling, I would go directly into the falling state. And we would cover simple logic like, hey, if I have a specific state tag or whatever else, I can basically say go into a specific state. This will greatly simplify a lot of your setups, because previously in some anim systems where I've worked in, to go into a specific state, you have to start always in the same entry state and then have transitions to the intermediate state and then transition back into a slide, which overcomplicates things and forces you to go through a shitty start state, which can sometimes mess up the pose. I mentioned state tags here. I discussed them in detail a bit later. Basically, all that you need to know for now, it's just a mechanism to know, hey, what state am I currently in the graph? So this is a kind of example here. I might have an idle, a walk state, and a run state. And if I click the entry state overrides, it's a node again in the state machine that you can just select, and it'll show up in the secondary view. And there you can basically say, hey, if my speed's between 0.10 and 2.5 meters, you know, go into the walk state. If my speed's greater than 2.5, go directly into the run state. If I don't have any speed, i.e. it's less than 0.10, then just go into idle. That's the default, and that's what it's going to do. It's a very simple way to just remove a bunch of like complexity in your graphs by you trying to force transitions. Additionally, you often have this setup where sometimes, let's say you're doing a combat game like a brawler or something, you might have an attack state machine with like 10 attacks, and every attack can be chained with any other attack, and that's so basically every state can go to any other state. And then you end up with the spaghetti. We have a very simplified mechanism to solve this. You simply just have a set of global transitions, which are within the context of a single state machine. So imagine we have this basic setup where, you know, A, B, C can basically go back and forth within each other, but then there are some specific things where C can only be followed by E, D can only go to, you know, A, B, C, and there's some extra complexity there. It's not just everything to everything, right? So what we do is we basically say, for the states that everything can go to, we'll make a global transition. So in this case, we'll create a global transition, which is defined primarily by the little arrow, the little lightning bolt. And it basically says, hey, basically, sorry, like I'm losing my train of thought. So it basically says an global transition exists for this. So everything can go to this state. And you have to look at the global transitions to figure out what the conditions are, but anything can go to the state. But you'll see that these red arrows as well. That basically says, hey, you need to block this transition. So even though there's a global transition, so anything can go into D, if you're in C, there is a blocked transition to D. So that will override the global. In the case of E, you'll see that there are white arrows too, and those are specific overrides that say, you know what, yeah, there's a global transition to E, but from C to E, it needs to do a very specific transition. So I have to use a different set of settings there. So again, this feature basically allows you to specify that everything can go into everything, but it allows you to also block specific transitions and override specific transitions. So I think I actually have this in the engine that I can kind of explain. So this would be a very kind of basic example of a combat state machine. You have a bunch of attacks. Every attack can go to every other attack. There's a million transitions. Whenever you set up, I haven't set up conditions here, but a lot of the time these transitions will all be like copies of each other. For example, A to C will be if my attack ID is C. The transition from E to C will be if my attack ID is C. And so you'll copy paste a lot of those transitions everywhere, which again ends up being error prone, means every time you want to change something, you have to change 15 different places. It's easy to make mistakes. It simply doesn't scale. So with the global transitions, this basically simplifies to this, where if I go to my global transitions, these are basically transition nodes that I can basically just set up whatever transition logic I want, whatever conditions I want. And I can basically see that, hey, D has a global transition, so I know within the context of the state, everything can go into D. There's no issue. If I wanted to block a transition from D to E, I would just make an empty conduit. And that would say, hey, there's a conduit here. It means that somebody explicitly made this. So there's no global transition anymore if I'm in D and I want to go to E. And if I wanted to override it, I would just simply create a new transition here, and you'll see that the color will change. And now I have a valid explicit transition. So it gives you all the flexibility of manual transitions, as well as blocking transitions, as well as removing all that horrific noise and duplication of conditions in like 50 places. This alone will simplify, well, will remove 90% of the issues that people have with state machines. We're like, oh, it's too complex, I can't manage it, it's just a mess. Yeah, just do the simple thing and fix it in tooling. Now we get to another common headache, communicating between animation and gameplay. Gameplay needs to know what state the graph is in a lot of the time, because they'll issue a command like, hey, you need to do a jump. But gameplay doesn't exactly know when that jump is finished or when the graph is even in the jump loop. You know, it needs to have that information so it can react, it can send different information, it can handle the physics in a different way, what have you. In some animation graphs, you had to explicitly bind to nodes, and that was really, really clunky. You had to say, hey, I need to get access to this node, and you'd have to write the whole name and the whole path through and the entire hierarchy to get that node. And then you would query that node saying, hey, are you active? What state are you in? Blah, blah, blah. We have a different mechanism. We call it state events. Basically, what it is, it's an ID that a state can emit. And that ID is sent back to the game code, and game code can look at that and say, oh, okay, I understand from the state event what state the graph is in. And it's not bound to animations, because you could say, well, I could use animation events, but with the data set, you're constantly swapping in and out animations. There may be 10 variations. It becomes super error prone to have to go to each animation and put an event in there that says, hey, I'm now in blah state. So the idea is that if you put this in the state, well, you don't care about what data is in there, what that state is doing, anything else. It just says this state will emit these events in specific conditions. There are 4 different types. There's one that's emitted when we transition in. There's one that's emitted when we're fully in the state, so there's no transitions active. There's one that's emitted when we leave. And we have timed ones, which basically will trigger based on how much time I've been in a state or how much time is left in a state. And you can basically put multiple IDs for each one of those 4 categories. And whenever those conditions are set, those values will be sent out of the graph. So if gameplay wants to know if we're in a walk state, they'll say, hey, do I have a state tag for walk? Yeah, I do. Cool. Then that means the graph is walking. I don't need to know what the graph contains, how it's built, what the topology is. I don't care. I don't even care, like, it might not even be walking. It might be something else, but it's telling me it's walking. So this is what I need to know. And this is detached entirely from the data set. State events also have a huge benefit in that it can be used within the graph itself to know where we are and what we're currently doing. So in that example where I talked about the entry state overrides, they would fundamentally be checking those state tags. So we would evaluate the state machine and we would take that event. For example, if I'm in state A, I would evaluate state A. Then I would fire a transition to go to state B, but state A has been evaluated first. In state B, there might be a state machine that will then check its entry overrides, and it can then ask the graph, hey, has any state tags been sampled for this frame? So I'm trying to think if I have an example for this. I do not. But basically the idea being is that the graph will inform subsequent sections in the graph. Sorry, I'm a little bit less prepared than I normally am for these streams. I've been doing a lot of other stuff simultaneously, and I just wanted to get this out of the way. So here's a better example. I actually did it in the slides, not in the engine. We have certain tags emitted from the start states. So for example, when we enter the slide state machine, we can basically query and say, hey, were we crouched or were we standing? Because we would just ask for those tags, and based on that, we will pick a subsequent entry state. There's a comment saying global transitions is similar to any transition. Yes, it is. I don't know Unity's mechanism super well. The difference is that in my case, those global transitions are local to a state machine. They're not global to the entire graph. I know in other animation systems, they had this any transition, but it was global to the entire state machine. In my case, it's constricted within a single state. So you can have a global transition to any state within that state machine, but not anywhere else. So everything's very localized, same thing with the layers. It just makes it easy to reason about. I know one place they had these global transitions, but then it became impossible to manage because they would go from deep in one state machine to deep within another. And trying to figure out like why that happened, you ended up having to go through like a massive list of like 300 global transitions that people had created over time, where I find it a lot easier just to see it localized. Additionally, these state events can be used to block certain transitions. An animator can basically say, hey, I do not want this state to transition while this event is being sampled. And then he would set up a timed event that says, emit this event until we're 0.4 from the end of the state. So that allows them to basically specify something that we call cut time or something like this. It basically says only trigger transitions when you're within certain points of the animation. This basically allows you to do that, but at the state machine logic level and not embed this information into the actual animations themselves. What you're basically saying is, hey, like, do not transition out during these periods. Or potentially you'll say, I need to at least play 7 frames in a state before I'm allowed to leave. So what you'll do is you'll basically do a block transition event with a timed event that says, hey, if the time elapsed is less than 0.4 or a second or whatever, block all transitions, and all your transitions will then say, hey, if I have the state event, this transition is not allowed. again, it's just extra tooling to basically hint to the graph where to go, how do you transition, and those sort of things. And also to provide gameplay information, which means that you don't have to care about a tech enemy can go and restructure the entire graph. You don't care on the gameplay side. All you care about is that the events are emitted correctly. Sometimes we need to still put this information in animation events. This is the state events are meant for more high level stuff. Am I walking? Am I running? Am I in a stop? Am I currently in the jump? Those kind of things. A lot of times we still need to put events in the animations, like trigger a VFX specifically here, or actually block a transition for this specific period, which may change based on the animation. For example, like different archetypes might have different settles or different timings in their animations, that kind of thing. So what you would do is you'd put specific animation events in those animations that then the graph would check, because the graph still has access to the sampled anim events. So it can check and say, hey, this transition is only allowed if I have, an event of this type, or block this transition if I have an animation event of type block any event, block transition or something like that. The animators that are building these graphs have absolute control in when things can happen, which is how it should be. Now, the downside of that is that it's also like this becomes programming to a large degree. And it's not necessarily a mindset or a skill a lot of animators are familiar with. So it takes a lot of like education and working with them and guiding to get them thinking in that mindset of saying, hey, think about how you lay out your state machines. Sometimes you've put all the states on one level. It might be better to invert it and start creating more hierarchy. Or sometimes you want to just remove the hierarchy and create a separate hierarchy, like you would when you're refactoring code. And that's not a habit that they're familiar with a lot of the time. So they end up sort of trying to crowbar things in the initial kind of idea that they had. And sometimes you have to kind of sit with them and say, hold on, like, explain to me what's going on. Be like, okay, have you thought about inverting where these states go? Maybe you need to put them up at a level higher and put these ones low. And then they're like, oh shit, that simplifies everything. And then gets restructured. It is programming. And that's how you have to think of it. Now, the graphs grow to like massive, massive levels. At my last company, the graphs were in the range of 60K nodes, with 20 hierarchy levels, with dozens and dozens of state machines and that. And nobody got complained about complexity, or they didn't understand how things worked, or every time there's a bug, they knew exactly where to look. It was very simple and clear, fundamentally because the tooling was helping them to understand what was going on. They could kind of see why transitions fired. They could have very simplified setups with the global transitions or the entry states or what have you. And when something weird did happen, it usually took me like 10, 15 minutes to just debug it and say, okay, look, it's this bad setup, or actually gameplay's feeding you some garbage, so I'll fix it on that side. And this is kind of bringing me to a point that I'm not going to stay on a lot, which is the motion matching topic. Like, I was there at the start of this whole thing with Michael Butner and whatever, and fundamentally I'm like the one person that still, I think it's a good tool, but for very specific situations, people that are going all in on this is the animation system, I think it's a mistake. It feels to me a lot like it's a solution looking for a problem, where people either have no experience with good tooling for state machines, or are coming from really bad state machine based or no state machine based stuff. And this looks like a really, really good approach to a solution. Additionally, like, it is usually really complex. It's got a massive time investment in terms of programming. It's a black box that good luck if something goes wrong to debug, polish, tweak, or if something happens in the game, like you get a glitch and now they say, well, fix the glitch. And you're like, I don't know how. We have to retrain it. We have to adjust data and that. And a lot of the time, once you go into production with these things, you end up building a pseudo state machine, because you start tagging up your animations to separate them out into separate buckets, and then you motion match on those buckets. And there's a whole bunch of stuff here that fundamentally, like, I know what it's trying to solve, which is the state machine problem of like the complexity. But my counter argument is if you have good tooling and a good setup, well, that solves the problem easily enough, and everybody has explicit control. So if an anim director comes in and says, I need a very specific transition between these things, you would just do it. So if you're building an animation system, motion matching can be a node in the graph. But my advice is you start with a graph, you build the graph, you make sure that that is working, because now you've secured it. You've secured the project, you've secured the tooling. There's no risk right now. And now you can spend time investing in motion matching and playing around with it and seeing where it can be used or not. But going all in on this and saying, graphs are just old school, fuck them, that's a mistake. So the more interesting stuff and where like the cool shit happens. Pose tasks. As I mentioned earlier, we have basically, the graph itself doesn't generate poses. The graph just spits out root motion and events. What it does do is it fills a command buffer with commands like sample, blend, run IK, do some physics. We've separated this out for various reasons. The most obvious one is physics, and I'll get to why we had to split this out for physics. But splitting it out also adds some benefits in terms of LOD and performance. So let's do some basic examples. So the pose tasks themselves, what they are is an atomic pose operation. It just creates a pose or modifies a pose, nothing else. Input pose or zero input, output pose. That's it. It may have a physics dependency. Some tasks have to be run pre-physics, some tasks have to be run post-physics. For any task that has dependencies, it explicitly specifies, hey, I have 2 dependencies or 1 dependency. And they're polymorphic. So again, we have derivation and some virtual functions. Everything in the graph is virtual functions and whatever else, because it's just simpler and there's a lot of shared stuff and there's a lot of simplicity there. So let's look at a very basic example of a blend tree. If I have 2 animations that I'm reading and then I want to blend them, and then I want to take that result and I want to blend it with another animation, well, we generate a task list that basically says, sample AB, then register a blend task with the dependencies 1 and 2. You'll see that the samples don't have dependencies because they're the source. Then we'll sample C, and then we'll blend it, but the dependency now is 3 and 4. And as we go through our nodes in the graph, when we're spitting out the pose result, what we're returning is the task index of that specific node. So we would, for example, in a blend, update our child A and get back 1, and update child B and get back 2, and then say, oh, I'm going to register a blend task for task index 1 and 2. Same thing for the secondary blend. It would first ask the blend node 3 and say, hey, what's your task index? Okay, it's 3, whatever. And then it'll update C and say, okay, it's 4, and then those are my dependency, and register that out. So the task system, this is the thing where we register our tasks, and has a pose buffer pool. And this is a big win for performance where, for example, tasks will request, they will free, and they will transfer pose buffers amongst themselves. The pool will grow if we request more poses, but on average, we need roughly 5 poses per pool. This is a massive win because, again, poses are pre-allocated. We're not allocating them dynamically or anything like that. So how does this work? Well, for example, sample animation A with a simple, again, blend example. We'll say sample. It'll say, hey, I need to sample an animation. Give me a buffer. Gives them a buffer back. Cool. Sample B says, you know what? I need to sample animation, so I need a buffer too. And it asks for a buffer. The blend says, well, I need to read those 2 results, but I also only am going to expose 1 buffer. I don't need my own buffer. So I'm going to transfer X to me. Now I own X. And then I'm going to free Y. So I read the results of X and Y. I will write the result into X and then release buffer Y. So what that ends up doing is basically you end up reusing buffers as you go along the traversal. So for example, if I had a node that just modified a pose, I would just transfer the buffer from, Sample a thing, transfer the buffer to the modifier, modifier will modify the buffer directly, and then transfer it onwards. So for example, we might have a more complex setup where we're running a lot of layers and transitions and blah, 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 and this results in sort of a crazy blend shoot like this. How many poses do we actually need to resolve this? Right? You look at it, it's like what, 1, 2, 3, 4, it's 12 samples and a shit ton of blends and stuff. We only need 4. You only need 4 poses for this entire thing to run. And the pose pool is also why we track the task dependencies, because we need to transfer the buffers between the poses. And you will think that, okay, this must be kind of crazy and kind of complex on how to build this. But it's actually ridiculously simple. So for example, this is a sample task. That's literally the whole task. We basically do the execute, which says, give me a pose buffer. And then we say animation, give me the pose, stick it in that buffer. There is your sample. A blend, that one, right? The blend must be complicated. Well, not so much. What I do is I transfer the first buffer. I access the target, I blend the two, and then I release the target buffer. And that's my blend. It's, again, very simple. You don't need a lot of complexity here. And this buffer system actually saves you a ton of perf in terms of not having to allocate a bunch of poses and reusing the poses. So let's talk about the ICAM physics, which is one of the main kind of reasons why this pose buffer system was sort of built. ICAM, I'm not going to do too much detail. Basically, all it is you take a pose, you modify the pose. Generally, it's stuff like I want to attach feet to the ground or lock hands to certain points in the world, that sort of thing. It's generally treated as a post process. We're going to come to that in a bit. So if we want to talk about IK, we need to also talk about how gameplay calculates IK targets. This is sort of, we would generally run the simulation first. We would move the character. We would then calculate animation, which is a skin on top of the actual simulation object because we've actually moved the simulation object already. And then we would run IK as a post process. And this works because you've moved the character. Animation might slide or whatever, but it's again tied to the simulation object. And then based on that position, you then run the IK. Everything works. When you go into anim driven, things become a little bit more complex because your character physics is not actually moving your character. It's doing a prediction step. It's saying, hey, I think you need to do this. You're feeding it into the graph. The graph is calculating a pose, but it's also getting a root motion delta out. And then you have to take that root motion delta and then move the simulation object with that. And then run IK as a post process. So you have to remember that you have to run IK after you've moved the character. Otherwise, whatever points that you specified in the world may not be accurate, especially for something like footsteps. Well, you thought the character was in one position, you calculated your targets, and now the character ended up in a completely different place, and now your target calculations are wrong. So you have to be very careful about when you do your IK. Personally, I think IK as a post process is wrong. It's a very old school approach of I do my animation and then I run my IK. It has a lot of problems if you do that. Because at the end, you're basically trying to solve the entire IK problem in one pass, which is problematic. So for example, super basic case, you have a crowd character that basically walks around and potentially looks at different objects in the world. When the targets change, how do you blend the targets? Right? Who is doing that work? It's well, you were looking at X and now you're looking at Y. Who is basically making sure that that IK transition is smooth and doesn't just pop the head or doesn't go down a weird path or whatever else, right? That now has to be handled in the IK system. Somebody there in code is managing, oh shit, the target changed, so I'm going to slowly blend it. I'm going to make sure it follows a good path so that the head doesn't do something fucked up, because if I potentially have a target, I'm going to try to do it on camera here and a target here, the shortest path might go, through the head. And so you might get a weird IK result trying to just snap the target like that. So you often have to drive it in a sensible way, and that's complicated. Additionally, like, what if a character was in a specific state that modified the pose, and now, like, what is my IK calculated relative to? It might be like the body might be tilted, so I can't really calculate targets in local space or whatever else. It adds a lot of complexity. Additionally, there is also a problem of what if I have multiple requests for the same body parts? Which ones do I take? Which ones do I blend? Do I blend them? Should I blend them? Should I just overwrite them? Right? It becomes a whole system of its own of trying to manage all of this. And frankly, like, you don't want code dealing with all this, because now some programmer has to figure out, well, I have a look at target, and then I have a combat look at target, and then my feet are being IK'd, but then I'm supposed to do this other IK thing, so now I have to turn it off here, and it becomes a mess. And then animators will constantly be like, well, this isn't doing what I want, turn off the IK, let's, there are better solutions. So what I tend to do is I tend to build more bespoke IK solvers that solve a very specific problem, not the general case, not a full body solve. It solves a specific localized problem. And then I create nodes for that in the graph. So we also provide targets from the outside. So if I have multiple lookats, for example, I might have a ambient lookat set, a reaction lookat set, and a combat lookat set simultaneously, because what may happen is that I might be a crowd character or something walking through a scene, and I've been told, oh, look at this billboard, and I start looking at the billboard, and then all of a sudden the player throws a grenade or something that's an explosion. So I'm being told, no, maybe not explosion, but the player makes a noise. So now I'm being told react to the noise. So I have a different lookat. And at the end, it's like, okay, my lookat goes to the reaction, and now it ends. I have to go back to my ambient. You don't want a system in code managing all of this shit. It's just annoying. You just basically want gameplay to say, you have an ambient lookout target. I'm going to tell you when it goes away. Oh, you have a reaction one, two. Here's a reaction target. And then the graph will determine, hey, I have all these things set. Given my current state, which ones can I act on? Which ones can't? Which one makes sense? That kind of thing. You let the graph take care of the visual aspect of this. Code just tells you, here's all the shit. Figure out what makes sense. So what I end up doing is I make nodes for this thing. So we will have multiple IK nodes in the graph. So for example, I will have an ambient node that has a lookat that basically says, hey, for the ambient pose, do this lookat. And then when we transition to a reaction, the reaction state might have its own lookat that does a thing there. And what ends up happening is you end up resolving the IK immediately, and then you just do a blend, which generally you've already done the lookats twice. So you have two poses that are looking at the correct things, and you're just blending from one pose to the other. And that's a well-defined thing. You know what it's going to look like. So now you don't have to do with this crazy, oh, I need to blend my target in space with certain velocity. You don't care. You have two poses that are looking at the right things, and you just blend the poses. And what that ends up looking like in the task system is this. You have a sample and IK. Sample, IK, blend. It's super simple. You might think, okay, well, IK can be expensive, but again, your IK is not a full body. Your IK is doing a very bespoke thing. So writing a lookat IK is not a very complex thing. And you don't have to do full body, so you don't have to do a complex simulation. Like I've written ones that basically just modify some chest, some head, spine, whatever, and it's microseconds. And if we look at the lookat example, another headache that if you don't split things out in the way that I have that can bite you in the ass is if you embed IK in the graph, you run into the problem where is the character in the right position when I evaluate the IK? And if you don't have a task system, the answer is no, because animation runs between when I predict the movement and when I actually perform the movement. So during the graph, my character's in the wrong spot. It's in the previous position, which is why the IK used to run as a post process. So in my setup, it's as simple as basically the graph will generate the post task. It'll say, hey, you need to do IK. Register the IK tasks. It will calculate the root motion. It will move the character, everything. And then you will run the pose task on the final position of the character for that frame. This is why the root motion is coming from the graph and not calculated via the pose. Initially, in one of my earlier iterations of the system, the pose tasks were also calculating the root motion, but that led me to this problem where I had discrepancies in the IK and in physics. So the root motion now comes from the graph, which frankly I think was the correct thing to do, and I don't know why it took me so long to realize it, because it has certain other benefits too. The nice thing is when you do this, when you run the pose task, you're still calculating the pose individually and applying the right IK and blending the poses, not the IK targets. You don't have any frame lag, you don't have any overreach because you're at the right position, all that kind of stuff. So it solves a lot of those headaches. It also allows you to use IK for animation synthesis. In many cases, we were generating animations via IK. We would create a broken skeleton because we would offset certain parts of the body and then run an IK solve to basically reconnect and refix the skeleton. And we would basically generate animations sort of like height adjustment, leaning left and right, those sort of things procedurally in the graph using IK. And then that was done on a per state level. So when we blend it out, it was a trivial thing because we had a fixed pose that was, completely valid. And we just did an animation blend. It also means that you can fix IK when you need it. So in cases when we do weapon handling, I may have some sort of a weapon where I need to procedurally adjust the hand distances together based on the length of the weapon. And then I need to blend between this and a different weapon handling state or a different position of the weapon. It's a lot easier to just fix the hands and blend to another pose with fixed hands than to try to, fix this the whole way through that blend process. You end up with a lot more control. This is another thing. They can turn on and off IK when they need it in the graph. They can blend it in and out however they need it. They can ignore it if they don't want it. They can use animation events to turn it on and off for a specific state based on what the animation is doing. Like they'll say, hey, for this portion of the animation, I don't want IK. So they'll feed an event back to the IK node. They have a lot more fine-grained control over this than if they had a final solver at the end where now they have to explicitly, drive that. Sorry, my allergies are like kind of killing me right now. Let's go on to physics. That's another fun topic. In my setup, Ragdolls are actually integrated into the graph. They're also not a post process. We also don't have a single Ragdoll per character. What we do is we actually dynamically create Ragdolls when we need them. So we create a simulation Ragdoll for a given state. So what we do is we can create very bespoke setups of Ragdoll saying, hey, this is a Ragdoll that just has the upper body, or hey, this is a Ragdoll that just has the lower body, or this is a full body one, or whatever. And whenever we activate that specific node, we instantiate that Ragdoll. It's surprisingly inexpensive. If you use the PhysX articulations feature, it's really, really cheap, and you get some really, really good results with it. And so this is, again, where the post-task system comes into effect, where it allows us to split our tasks pre and post physics. So, for example, we'll do a simple blend of two animations. We'll feed that into a powered Ragdoll, and then we can layer animation onto the results. So that's another cool thing, is that I can take the results of a Ragdoll and apply a blended animation layer on it, or do an IK pass or something. Hell, I could blend it with another animation state. So what happens in the task is that we will have that powered Ragdoll node register two tasks, one that runs pre-physics and one that runs post-physics. And so as you can tell, and then that splits our task list around the physics tick, which again, this part is relatively self-explanatory. And as I said, you can just chain IK on there, whatever blends you want to do, it doesn't matter. It just runs as part of the graph. This allows us to interleave physics with FK and IK. It also means that we can drive a powered Ragdoll with a really complex anim state. We can then apply contact paths to the physically simulated Ragdoll So for example, we can get some secondary motion and still do an IK correction pass on it. It also means that we can blend from ragdoll to ragdoll. This is something interesting. You don't need to now handle this at a ragdoll level of trying to blend profiles and shit like this. You just spawn two ragdolls and you blend from one ragdoll to another ragdoll. And that is a very well-defined operation because you're just blending anim poses. You're running two distinct ragdoll simulations with very different settings, with very specific setups, and you're just blending the results. So how does that work? Well, it's as simple as that. You have one state that has a ragdoll, another state that has a ragdoll. You do a blend. So the task list basically says set the desires, which are pre-physics tasks, and post-physics, we read the two results and we blend them. And this, again, comes for free with the post system and the way that the graph is built. Now, there's an obvious restriction that you cannot change ragdolls together. But again, this isn't a problem. There's no use case that you want to take the physics results of one ragdoll and feed into another ragdoll to drive a ragdoll. It just doesn't make sense. Additionally, that setup is checked by the graph compilation. So the graph will throw an error usually and say, hey, you can't chain these nodes together. Or, within a single blend path, you have multiple ragdoll nodes, so this is not okay. And then you can fix that. Another thing that really helps with tooling and complexity is what I call external graphs. Basically, I don't know how many people are familiar with smart objects or smart terrain points or whatever your company calls them, but basically it's objects that are placed in the world that have some set of animations bound to them, like, you want to put a park bench that has like, characters go sit at, or a chessboard where they can play chess, or an ATM that they can use, something very specific, and the animations are tied to that specific object and not to the character. Naively, some people will put all the animations into the main character graphs, which is kind of insane because you have to load all that data, even if those objects don't exist. And as you try to scale, this doesn't work really well. So we solve that using external graphs, where you basically create a graph for each one of those setups, and then you can inject it at runtime into the main graph. So for example, what you would do is you would set up some slots in your main graph that says, hey, this is a smart object slot. So you can inject a smart object onto here. Normally you'd set up like multiple slots and you'd have blends between them, so you could go from one smart object to another directly. And then gameplay will say, hey, you want to use a smart object? Cool, I'll load the graph for you with the smart object and all the animations you need, create the instance, everything. I'll then inject it into the slot, and then I will drive the graph. So gameplay will then drive that external graph because it's loaded it, it knows about it, it can manage and say, hey, this is a very simple smart object graph, so I just have to inject it and let it run, and it'll tell me when it's finished, and then I remove it. Or it will say, hey, this is a turret, so while it's using the turret, I'll have another piece of gameplay code that's managing target selection, firing, reloading, whatever, and driving that external graph with parameters. And the main graph at that point just says, I'm in a slot, I just feed out whatever that slot does. I don't really care, my parameters are not doing anything, I'm just executing whatever's there. This also allows us to basically specify control parameters however we want for these injector graphs. They don't have to match the main graph. They don't have to do anything. They're completely detached. Once you do this, you can manage how much data you load, when it gets loaded, like those sort of things. You also don't pollute your main graph with all this crazy complexity of like whatever random shit can be placed in a specific level or a one-off or those kind of thing. It also provides like parallel workflows. You can have a whole bunch of people building these separate graphs completely in parallel and test it in parallel, whatever. You don't need to modify the main graph and that kind of thing. That's a kind of very basic thing. I think a lot of systems have this to some degree, though a lot of it is very clunky or complicated for no reason. This should be built into your system by default. It should be a very simple mechanism that everybody understands how it works, and then again controlled. It's the same thing for sort of cinematic animation that's also done via a slot in the graph, where it's like, hey, here's a slot that basically is a source pose provider. We'll switch to that thing, and then we'll have the cinematic system feed a pose into there instead of like trying to switch you away from your main graph into something else and then come back and whatever else. Everything for my system is done via the graphs. The graph is the animation system. There's nothing else. There's no switching out of it. Everything that is external is still linked in via the graph. So we're almost at the end. We're going to talk about performance because this is an area where a lot of people will start being like, well, you said everything's virtual and it looks very OO and blah, blah, blah. I'll show you some numbers first, and then we'll talk about perf. So these are numbers coming from an old cancelled game. And they're fundamentally, I think they're coming from a PS4 because these numbers are from way before the PS4 Pro even existed. And the graph was around 16K nodes. There was no optimization done. This was just numbers I took midway through production just for myself to check. The graph was running at around 20 to 60 microseconds. That was the full graph evaluation of those like 16K nodes. The tasks themselves with a bunch of blends, usually we were blending like 4 or 5 things per frame because we were layering a bunch of stuff and whatever, was around 30 to 50 microseconds. So we're talking around 50 to 100 microseconds for the full animation update. That includes sampling, decompression, root motion, event sampling, all of that on a PS4, right? And again, these are really old numbers with a slightly worse version of this whole system because I've optimized and improved a lot of stuff since then. But these are the numbers that you should be getting for an animation update, right? Not these like half millisecond, 2 millisecond insane numbers that some of these motion matching systems are doing. Like this, it should be an order of like, nowadays on the current gen consoles, those numbers are even lower because the Jaguar CPUs were really, really slow in the Xbox One and the PS4. So these numbers are much lower right now, but I don't have any numbers that I can show you from that because, again, NDAs and stuff. So how do we get that performance? Well, one, there's no allocations. The graph, when it's instantiated once. We do not allocate any memory at runtime. If we have any dynamic arrays, those are usually inline, so we pay a little bit extra memory, but we just don't have, we don't use dynamic arrays fundamentally, so we're not jumping out of memory every time we hit an array. Warping does alloc. That's the one thing where if we need to do a warp, we have to allocate memory for the root motion track and so on. Ragdolls, obviously, when we instantiate them, that does alloc. So those are the only 2 areas where we really allocate during runtime, and that's very kind of limited. The nodes are laid out in a single memory block, and they're ordered by traversal. So child nodes are laid out after the parents. So primarily when I'm in a parent node and I say, hey, give me the child, it's usually directly in memory right after that thing. So again, it's built in a more cache-friendly approach. We also only evaluate the nodes we care about. We don't need to evaluate a whole bunch of the graph or whatever. We just drill down into the bits we need, we evaluate those, and we're done. And again, everything's virtual functions, everything's simple OO mechanisms, that sort of thing. It's like, I haven't gone to any massive detail to micro-optimize anything, and the numbers are pretty good. I would argue they're outperforming a lot of other production anim systems at the moment. Additionally, one thing that helps us a lot is we have 2 node formats. I have editor-only nodes that basically have a much heavier representation. They may have separate bools. They may have more enums. They may have a whole bunch of settings that are beneficial for the user because the user wants to have a bunch of options and stuff like that. But then they get compiled down into a much more compact runtime format. So for example, I might take like 10, 15 bools and then bit pack them into a byte array. I'll take a bunch of enums, the bools, everything, and then I'll have like a 16-bit bit field. So we basically have 2 formats, which allows us to provide the users whatever nice tooling they need, and then have a very optimized format. We split the settings of the node and its instance data. When we load the graphs, we basically load the definition of a node that says, hey, this is a node of this type and these are the settings that it has. And then we create an instance, and that instance refers back to those settings. So if it needs to say, hey, what were the parameters that the user authored, it refers them to that. So we have those parameters once in memory, and all the instances just refer to that data. So again, that keeps the graphs instances relatively lightweight as well. And as I said, we placement new them into that initial block of memory. We then set up like whatever pointers based on that block of memory. We basically do a pointer fix up because we serialize indices saying, you know, like node 17, its first child is 5 and its second child is 15. And we just fix up those pointers during the instantiation step. And then we just run the graph. Splitting out the task list. That was actually kind of a nice thing because I have the root motion now when the graph evaluates. That basically means that the poses are entirely optional in many cases. If a character is super far away, I don't need to evaluate the animation pose. You know, I don't have to do that. I could also run a pass through my pose task and say, you know what, like all I can ragdoll, I'm going to strip it out. We don't care, right? The character's off screen or it's far away. Don't need to run those tasks. Having that pose task list as a separate thing allows gameplay to fundamentally function as if everything was behaving properly, but we don't need to evaluate any of the actual like expensive IK post tasks, whatever we need to do. But we still know what state we're in due to the state events or whatever. We have all the anim events and we have the root motion. That also gives us a big opportunity to play with that data without changing any of the graph logic. And that's also been beneficial because we can run an optimization path and say, you know what, like for this set of characters, I'll have an LOD profile that just basically doesn't run any of the post tasks, for example, a crowd or something. As soon as they go off screen, don't need to calculate poses. But maybe for AI, we still need to calculate poses because we have to update hitboxes or whatever we have if we're running on the server. Then potentially we don't need to run a bunch of, you know, head look ats, whatever else we need to do there. You know, anything that's major, we have the choice there to adjust that. So that was kind of a long brain dump. I feel like I wasn't super prepared this time around. As I said, sorry about that. I've been juggling a million things at the moment, but I just wanted to kind of get through this. If there's any questions, there doesn't seem to be too many right now, but if they are, you could always just poke me on Twitter or whatever. If you want access to the source code for my stuff, like I'm more than willing to share it, but be aware that it hasn't really been tested in my home engine or stress tested or whatever, so it's kind of like rough. And at some point I'll go through it and like make sure everything 100% works, but right now I'm not guaranteed for it, but it's a good reference to at least see how it's built and how it works. So yeah, that's it. If there's any questions, doesn't seem to be any right now, hit me up on Twitter. And otherwise, have a good weekend and take care.